Welcome back. This is the second part of section 2.2 about the geometric forms of the Hahn-Banach theorem. So in the last video, we formulated the problem that we are interested in, and it was about separating two convex disjoint sets by a closed hyperplane. The first result is the first geometric form of the Hahn-Banach theorem. Okay. So if A and B are disjoint, non-empty convex subsets of a normal space, and one of them is open, then we can separate them by a closed hyperplane. Okay, for the proof, we need to establish two intermediate results, one of them being a particular case of theorem 2.2. Okay, the first lemma is about the Minkowski function of C that we defined in section 2.1 as an example of a subnorm. Okay, so if we have an open and convex subset set C of a normal space E that contains 0, we set P of x to be the infimum of the all positive numbers alpha, such that 1 over alpha x belongs to C. And P is called the gauge of C, or the Minkowski functional of C. Okay. Now we'll prove in this lemma that P is actually a subnorm according to the definition that we gave in a previous video. Okay. So the first property is that P is positively homogeneous. Second property, it's sublinear, so it satisfies the triangle inequality. And third property is that this function, of course, is bigger or equal than 0, but this is trivial because it's the infimum of a set of positive numbers, and it's bounded by a constant times the norm of x. And last property, C is actually exactly equal to the set of points whose image under P is strictly less than 1. Okay, so let us prove one. So we go back to the definition. So we write P lambda x is the infimum of the set of positive number alpha, such that 1 over alpha times lambda x belongs to C. Now, so you can write it as lambda over alpha x, or if you like, 1 over alpha over lambda. And the alpha, we can write it as lambda times alpha over lambda. And now we do a change of variables, if you like. So we can, if you put alpha over lambda equal beta, so it's the infimum of lambda beta positive, such that 1 over beta x belongs to C. And since lambda is a constant, you can put it outside the infimum, as you may check. Okay. So when we put it outside, we get precisely lambda p of x. Okay, so this is really trivial. So this is positive homogeneity. Now we'll prove actually 3 and 4 before we prove 2, because it's the proof of 2 is a little bit tricky. Okay, you cannot prove it directly, so we'll prove that P of x plus y is less or equal than P of x plus P of y plus is a positive number, epsilon or 2 epsilon. Okay, so let us prove 3. Okay, since C is open and contains 0, there is by definition a ball around 0 contained in C, and we can take it closed, we can take it open, doesn't really matter. We proved that. What does this mean? It means that whenever the norm of x is less or equal than r, then x belongs to C. It's just the inclusion. So in particular, since the norm of r over norm of x times x is exactly equal to r, then this guy belongs to C. Okay, and therefore we can write this guy as norm of x over 1 over norm of x over r times x belongs to C. So the elements x over norm of x over r belongs to the set. Okay, so here instead of alpha, you put norm of x divided by r. Okay, so norm of x divided by r belongs to the set. And therefore, it's bigger or equal than the infimum, because the infimum is a lower bound. Okay, so norm of x divided by r, since it belongs to the set, it's bigger or equal than the infimum. So P of x is less or equal than norm of x over r. So we can take m to be equal 1 over r. Okay, so this proves 3. Now we can prove 4. We have to, so there's a double inclusion or double implication. Suppose first that x is in C. We have to prove that p of x is less than 1. Once again, by openness of C, there exists an epsilon small enough such that x plus epsilon x belongs to C. Okay? Because if you do the difference between the 1 plus epsilon x minus x, you'll get epsilon x. So if epsilon is small enough, then the difference belongs to a ball of center x. Okay, so when I perturb x by a small enough term, openness exactly means that we will be still in the set C. Okay, therefore, once again, I can write the 1 plus epsilon as 1 over 1 over 1 plus epsilon. Right? So 1 over 1 plus epsilon belongs to the set under consideration. So it's bigger or equal than the infimum. And 1 over 1 plus epsilon is, of course, less than 1. So p of x is strictly less than 1. Okay, so this proves one inclusion. Now, conversely, suppose that p of x is less than 1. You have to prove that x is in C. By a fundamental property of the infimum, there exists alpha in the set that we talked about, such that alpha is less than 1, so it's less than the infimum, and 1 over alpha x belongs to C. So this means that alpha belongs to the set, but it's strictly less than 1. Okay. So now we can write x as alpha times 1 over alpha x plus 1 minus alpha 0. So this is a convex combination of 1 over alpha x and 0. And now convexity of C, here where I used convexity, 0 is in C, 1 over alpha x is in C. So this linear this convex combination also belongs to C. So x belongs to C. And this proves the reverse inclusion. Okay, now we prove 2. Take two arbitrary elements x and y in E and an arbitrary positive number epsilon. By positive homogeneity, which is property 1, I can put this real number. This is a real number because p of x is a real number, epsilon is a real number. So I can put this constant outside. And we get 1 over px plus epsilon times px. So this ratio is, of course, less than 1. And by the previous property, this argument inside P belongs to C. And similarly, y over py plus epsilon also belongs to C. Convexity of C implies that any convex combination of these two elements belongs to C. In particular, if I choose T to be px plus epsilon over px plus py plus 2 epsilon, this number is, of course, between 0 and 1. And when I replace T by its value, I get 1 over px plus py plus 2 epsilon times x. And the other one will give me y over px plus py plus, as you may check easily. Okay. And now I use both property 1 and 4. If this belongs to C, then its image under P is less than 1. Okay. But by positive homogeneity, I can put this constant outside. Okay. So I get p of x plus y divided by p of x plus p of y plus 2 epsilon is less than 1. And if I multiply by this, I get this inequality. Okay. And this is true for every epsilon, since epsilon was arbitrary. Or if you like, if we let tend epsilon, we fix x and y, and we let epsilon tend to 0, we get the large inequality p of x plus y is less or equal than p of x plus p of y. So this proves that this is a very important example of a subnorm that we discussed in section 2.2. Okay, so this concludes the proof of this first result. And we'll explore more properties of this Minkowski functional in the exercises in the next video. Okay, now the second result before we go to the proof of Hahn-Banach first geometric form is actually a particular case of that form. So once again, we take a convex non-empty subset C of a normal space E, and we take an element x0 not in C, in the complement of C. Then we can separate C and the singleton x0 by a closed hyperplane. So if you put f of x0 equal alpha, then you have f of x less than alpha for all x in C, and f of x0 equal alpha. Okay. So this is really a particular case, but we'll be able to deduce the general case from this particular case. Okay. You can draw a figure actually if you like. You take a convex set, an open convex set C, and x0 outside C. It could be at the boundary actually, and so this separation is not strict here actually, and there is no epsilon involved. So I encourage you to draw a figure. Okay, take a convex set C and point x0 outside, possibly on the boundary. If it's on the boundary, you draw just a tangent to the convex. Okay. Yeah. Now, we may assume after a translation that C contains 0, so we can use the Minkowski function. Okay. Why we can do that? Because since C is not empty, take a point A in C. And so you can draw a figure actually if you like. So you take A, and when we translate C by A, then x0 minus A will also be outside C minus A, but now the 0 will be in C minus A. Okay, so you can draw a picture actually to understand what does so. Okay, so we translate the figure if you like, so that 0 is now inside C. Okay, so now we can define the Minkowski functional P of C. And we consider the linear map or the linear form from the one-dimensional space spanned by x0 into R. How to define it? So any element in this one-dimensional space can be written as t times x0, where t is a real number. It's not necessarily restricted to 0, 1. So just any real number. And we set g of t x0 equal t. This is well defined actually, because any element in this space can be written in a unique way in this form. So if you like, t is the coefficient of x0 or the coordinate along the basis x0. Okay, so now it's very easy to check that g is linear. Then say that, yeah, so it's linear, as very easy. But the most important thing that it satisfies the inequality that we encountered in section 2.1. G of x is less than this Minkowski functional for all x in G. Okay, how to prove that? Not terribly difficult, but it requires a proof. So take an element in G. This is the one-dimensional space G. So it can be written of this form, Tx0. Here we just have to distinguish between two cases. T is bigger or equal than 0 or T negative. Since x0 is not in C, then P of x0 by property 4 of the previous lemma, P of x0 is bigger or equal than 1. Okay? Because otherwise, if P of x0 was less than 1, then x0 would be in C. Okay? This is the contraposition. Okay. So, therefore, if I multiply both sides by t, I get Tpx0 is bigger or equal than t. Okay? So, or if you like, t is less or equal than Tpx0, but by positive homogeneity, I can put the t inside. Even if t equals 0, actually, if t is 0, this is trivial, okay? Because p of 0 will prove that actually p of 0 is 0. But at any rate, we know that p is bigger or equal than 0. So this extreme case is not really important. And therefore, we prove that, but t is g of x, right? So we get p of x is less than p of x. G of x less than p of x. Okay. Now, the other case, if t is negative, then by definition, g of x is just t, and this is negative. Now, the minus t is positive, and p is something non-negative. So the product, so positive times positive, if you like. Minus t positive, p positive, so the product is positive. And now, I use also the positive homogeneous, so I can put the minus t inside. So I get minus t times minus x0, but by the usual rules of a vector space, minus t times minus x0 is just t times x0, which is just x. So once again, you have g of x less, actually in this case, strictly less than p of x. Okay, and now you guessed where I'm going to. We are going to use the first geometric, the analytic form of the Hahn-Banach theorem. Okay, so we have now all the conditions. We have a linear map defined on a subspace satisfying this inequality, where P is a subnorm. Therefore, we can extend G to the whole space, okay, to a map that I call F that still satisfies the same inequality, but for every x in the whole space E. Okay, now, in particular, if we take x equal x0, then G of x0 is by definition 1. Okay, and since F extends G, then f of x0 coincides with G. So f of x0 equal 1. And we proved in the previous lemma that p of x is less than a constant time mx, time the norm of x. So f of x, this proves actually that f is bounded. Okay, or continuous if you like. And since if x is in C now, by the previous lemma, p of x is strictly less than 1. And therefore, f of x, which is less or equal than p, is strictly less than 1, which is f of x0. And this is precisely the inequality that we had to prove. Okay. So this concludes the proof of this intermediate lemma, which is actually a particular case of the more general case that we are now going to prove. Okay, so in the geometric form, we have two disjoint convex sets, A and B, and and we said that one of them is open. So suppose that A is open. Okay, we consider then the set A minus B, which is by definition the set of all elements of the form x minus y, where x is in A and y is in B. In the exercises, or even in the lecture of chapter 0, it's very easy to prove that C is convex. If you don't believe me, just prove it easily, actually, because A is convex, B is convex, then minus B is convex, and the sum of two convex is convex. Okay, and the second thing that we can deduce is that if A is open, then C is open as well. Why? Because we can write C as the union of all translate of A, where Y is in B. Okay, if A is open, then its translate is open. So A minus Y is open, and a union of open set is an open set, so C is an open set. And the condition that A and B are disjoint precisely means that 0 is not in C. Okay, so here we take actually instead of x0 is 0. Okay, so there's no contradiction actually, because in the proof we assume that 0 is in C, but here this was just for convenience. But here we take instead of x0 0. Okay, so according to the previous lemma, we can find a linear bounded map, so an element in the dual, such that f of z is less than f of 0, which is 0, because f is linear for every z in C. And we are almost done, because if z is in C, then we can write z as x minus y, where x is in A and y is in B. So I get f of x minus y is negative for every x in A and for every y in B. And by linearity, we get f of x minus f of y less than 0, so f of x strictly less than f of y. Now, therefore, in particular, the supremum of f of x for x in A is less than the infimum of f of y for y in B. Okay, we could have equality actually. This is why we don't have strict separation here. Okay, so, but at any rate, we can find a number alpha between these two numbers. Okay, and in this case, we have f of x less or equal than alpha, which is less or equal than f of y for x and A, y and beta. So the hyperplane f equal alpha separates A and B in the large sense. So this concludes the proof of the first geometric form of the Hahn-Banach theorem. And now we can give in answer to the second question that we asked in the previous video, when can we strictly separate? Okay. Of course, we have to put assumptions. Okay. So here are the assumptions. So as usual, convexity disjoint, of course, not empty. And now we assume that one of them is closed and the other is compact. Okay. Then yes, we can strictly separate them by a closed hyperplane. Okay. So put here closed. Okay. We are not really interested in arbitrary hyperplanes because an arbitrary hyperplane could be something really weird, like it could be dense. Okay. So here there is a missing word, by a closed hyperplane. Okay. So let us prove this. We set as before C equal A minus B. Then, as we know, C is convex. And second thing, C is closed now. How do you prove that it's closed? It's an easy exercise in topology that you probably encountered, but let us do the proof anyway. How do I prove that a set is closed? I take an element in the closure. So this is C bar actually. So I prove that the closure of C is contained in C. This is the strategy. So I take C in C bar. Then by the standard result in topology, we can find a sequence in C converging to C. Now this sequence in C is as necessary of the form xn minus yn, where xn is in A and yn is in B. Okay. Now compactness of B implies that yn has a subsequence that converges to some y. Okay. In order to avoid subscripts, we may still denote the subsequence by yn. Okay. So what do we have? We have xn minus yn is convergent, yn is convergent, therefore xn is convergent. And xn converges to y plus c or c plus y. Now, since A is closed and the sequence xn converges, then the limit must be in A bar, which is A, because A is closed. So x is in A. Therefore, we can write C as x minus y, where x is in A and y is in B. Therefore, C is in capital C. So there is just a C bar missing here. Okay, so this proves the closeness of C. Okay, and now we go to the proof of the existence of this hyperplane. Now, the fact that A and B are disjoint, as you observed before, is equivalent to the fact that 0 is not in C. Okay, because if 0 is in C, what does it mean that 0 is in C? It means that 0 can be written as x minus y, where x is in A and y is in B, so x equal y. If x equal y, so there is a point in the intersection. So, therefore, 0 belongs to the complement of C, which is open. Okay, so there is a whole ball in the complement of C of center 0, and I can take it closed. Okay, so there's something missing here. B prime 0. So B prime 0R is contained in the complement of C, and therefore it does not meet C. So the intersection is empty. Correct this, please. And therefore, I can apply the first form of the Hahn-Banach theorem, and I can find therefore a closed hyperplane separating in the large sense B prime 0R and C. Okay. Now it doesn't really matter, the order of the inequality is not really important, because I can also write f of rz is less or equal than f of x minus y, because I can replace f by minus f and alpha by minus alpha, because the hyperplane f equal alpha is also the same as the hyperplane minus alpha equal minus. So f equal alpha is the same as f minus f equal minus alpha. So the order is not really important here. Okay, but you have to be consistent, of course. Okay, so this is just, we are separating in the large sense this closed ball and C, and both, of course, are convex. And yeah. So now, since f is homogeneous, I can put the r outside. So I get f of x minus y is less than r times f of z for every z in the closed unit ball of A. So same symbol, B prime 0, 1 and B. Actually, if you are picky a little bit, you will have noticed that we didn't use the assumption, because we had to assume that one of them is open. Okay. This is not actually a big deal, because if B prime 0R does not meet C, then in particular the open ball B0R does not meet C. So actually we have to separate, not, yeah, but they are equivalent, because here actually we apply the previous theorem, we separate B0R and C. Now B0R is open, but as we know from an exercise, if a hyperplane separates B0R and C, then it separates their closure. Okay, so this is not really very important here. So. Okay, so we have this inequality: f of x minus y is less than r times f of z for every x in A, for every y in B, and for every z in the closed unit ball. And we proved actually that, so therefore the supremum of this guy is less than the infimum of this guy. And the infimum of this guy, you can put the r outside, of course, is minus the norm of f. And this is an important result that we proved in chapter 0, actually. Okay, so yeah, so we don't need to take the supremum, we just take the infimum, because we fix x and y, and we let z vary. So this is a lower bound of this infimum. So f of xy minus y is less than the infimum of r f of z. But as you know, we can, since r is a constant, we can put it outside the infimum, and therefore we get actually minus r norm of f. And this is true for every x in A and for every y in B. And now I take epsilon to be 1/1/2 r times norm of f, which is something positive, because f is not trivial. Okay, and if you rearrange that, so you get f of x minus f of y is less than minus 2 epsilon. Okay, so if we add 1 epsilon, this side we get f of x plus epsilon is less or equal than f of y minus epsilon for every x in A and for every y in B. And therefore, if I take alpha, therefore the supremum of this is less than the infimum of this. So I take alpha between these two, and this would be my hyperplane would be just f equal alpha, the same f as before, and this alpha in between. So we succeeded in separating strictly A and B by this hyperplane f equal alpha. So this concludes the proof of the second geometric form. And in practice, actually, we rarely use this form and with epsilon. We just write f of x strictly less than alpha, strictly less than f of y. Okay. So we rarely need this epsilon. But since we can prove something better, then it's okay. So now, remark, if we don't assume compactness of one of the sets, the result may be wrong, even in finite dimensional spaces. So here's an example. Consider the part of the plane which lies above the hyperbola 1 over x in the positive quadrant. Okay, so you can just please draw a figure if you like. Okay, so we have a hyperbola, and we have the part A above, but contains the hyperbola, and we take as B to be the lower half plane that contains the horizontal line y equals 0. These two sets are disjoint. Of course, they are convex, they are disjoint, and they are closed, as you may easily check. However, so we can separate them actually by the horizontal line y equals 0. But this separation is not strict. Okay, if we add epsilon or minus epsilon, so so the line y equal epsilon or y equal minus epsilon does not separate these two. Okay, so it's better to draw a figure here. So therefore, the assumption of compactness is needed, and we used it actually to prove that the difference is closed. And by the way, the difference of two closed sets need not be closed. This is why we needed compactness. Okay, so we are almost done, and let us conclude this section and this video with a very useful result that we shall use later. Consider a subspace F for normal space E, which is not dense in E, so its closure is not equal to E. Then there is a non-trivial element in the dual that vanishes on F. Okay, so this is the contrast here. So F does not vanish on E, is not the zero map, but it vanishes on F. Okay. How do you prove that? This is really interesting, and we asked it in the exam actually some time ago. So consider an element not in F bar, because F bar is not E. And now, therefore, we can separate the singleton x0 with the space F bar. X0 is convex and compact, and F bar is, of course, not compact. It's a subspace. It's closed. Actually, it's closed and convex because, once again, subspaces are always convex. Okay, so therefore we can separate them strictly by a hyperplane F equal alpha. Okay, therefore, in particular, for every x in f, f of x is less than alpha minus epsilon, but we don't need that epsilon actually here. Just need the fact that f of x is strictly less than alpha, which is strictly less than f of x0 for every x in f. Okay. So this is really a particular case of the previous theorem. Okay, so what do we have now? The linear map f is bounded from above on a subspace. Okay, so it's very important to work with subspace, but we proved in the exercise of chapter 1 that this implies that f vanishes on the subspace. If it's bounded from below or from above, it's necessarily 0. Okay, therefore this is 0, and that's it. This is what we proved. Okay, and of course f is not identically 0 because the hyperplane is not trivial. Okay, so that's it. In practice, we use this result in its contraposition form. So in order to prove that a subspace is dense, what do? We prove that there's no non-trivial. So if you do the contraposition, if there is no non-trivial map that vanishes on F, then F bar equal E. So which is equivalent to proving that if a linear continuous map vanishes on F, then it necessarily vanishes on E. Okay, so this is the methodology. Okay, we take an arbitrary element in the dual that vanishes on F, and we prove that it vanishes on E. Okay, we'll use this later in the course. Okay, so this is an important corollary of the second geometric form of Hahn-Banach theorem. Okay, so this concludes the video and section 2.2. In the next video, I'm going to cover section 2.3 and therefore finish chapter 2. So thank you for your attention and see you soon.